Okay, so last class we talked about approximate differential privacy. We saw Gaussian mechanism, which kind of gives us privacy when you only have L2 sensitivity as opposed to L1 sensitivity, right? And we also saw that Gaussian mechanism can actually be stronger than Laplacian mechanism in terms of number of samples you need, but weaker in that it only gives approximate versus pure differential privacy. Okay, and then we also saw advanced composition and DPSGD. Okay, and what we'll do today is kind of finish up the privacy part and then switch on to our new module or new topic, which is graphical models. Okay. So for privacy, so what did we start out with? We said privacy, the main takeaway should be privacy means proof, right? So if you want privacy, then you need a proof. Without proof, there is no privacy. It's not like, other aspects of machine learning where you can demonstrate that your system is working in some way or the other. For privacy, you need a quantitative way of quantifying your privacy, right? And differential privacy was one such method. Okay. And there's also the closely related pure versus approximate. Differential privacy. And then we also had various other sort of meta properties, right? We talked about post-processing, group privacy, basic composition, advanced composition. Okay. And then we had 4 sort of algorithms, kind of generic algorithms. I should say 5 actually. The first one was randomized response. Right, then we had Laplacian mechanism. Exponential mechanism. We also had Gaussian. And differentially private SGD, right? So where you're perturbing the gradient using Gaussian noise. Okay, so these are like, 5 maybe sort of central methods, and then there are many variants of it. You can combine them in various ways and get various guarantees, okay? So, differential privacy, as I said, is being used at various places in applied domains and in various systems, like US Census Bureau uses it, Apple uses it, Google uses it, but they don't exactly use the version that we are talking about. In some sense, it is a very good model because it is quantitative, but it has one central limitation. Can you think of any central limitation? Not quantitatively, but even just as a model, it doesn't fit some applications. Can you think of some applications? Yeah. Well, yeah, that's kind of affecting the accuracy. But I'm saying in terms of privacy, it still doesn't satisfy the privacy guarantees we'd want in some systems. Like, let's say you're Apple collecting data from phones. As a user, would you be okay to say, okay, I'm sending my data to Apple, and then I trust Apple to kind of handle it differentially privately, and okay, maybe Apple you would trust, but let's say Facebook, right? Would you trust them to handle the data well and not sort of give it to some other company like Cambridge Analytica or something? So I mean, what I'm getting at is differential privacy is a very good model under the assumption that we still need a trusted central party, right? So right at the beginning, in a definition, we said there is a curator who is holding the database, who collects the data from the individuals and is kind of, when we trust that person to handle it well, okay? This is not, for some applications, it's very good. Like if you're a hospital or if you're a person doing the study, maybe it's okay. But if you're collecting data from, millions and millions of phones, maybe it's not that good, okay? So this is kind of one other consideration, and there is a variant of differential privacy called local differential privacy. Okay, or LDP. I mean, we're not going to study it, but I just want to say that there are other variants which are interesting in their own applications. The local differential privacy is the setting where each user doesn't really trust the central party, but they're willing to kind of, give some noisy answers or, just send noisy data to the central party. Okay. So here you want, maybe let me draw a picture. You have the user, and then there is the database. And there is the queries, let's say, but want privacy here. Okay, so we want privacy for each user. Okay, even with how they interact with the database. So even the central party should not know very well what's happening. Okay. So the way this is modeled, any suggestions on how we might model this? And guesses? I mean, we kind of know at least some language of how to do this, right? You want to say that each outcome is kind of equally likely, no matter whether this person was in the database or not. That was the earlier formulation. And we can draw inspiration from that and say, no matter what my data is, the server should not have like absolute certainty on what I have, right? Any suggestions or how we might capture it? Assertion. Right. So actually, let's think of it even more fine-grained. This person is going to send some message here, Z, and the input is some V, let's say, right? You'll say something like, for all V comma V prime, distinct okay. So no matter what my true input is, the message that I send across is kind of, private. For any two inputs that I might have, there is some answer. I mean, the outcome I send is within e to the epsilon of the other outcomes. Okay. So you're taking it at a very fine level. I mean, in some sense, it seems like you're adding a lot of noise now. Excuse me. You are adding a lot of noise now because each user has to do something. But maybe if there are enough users, the database is still useful enough to learn something from it. Okay. Yeah.
Does this mean you have an extremely high probability?
Yeah, for sure. But the point is, like, somehow you're hoping that you're aggregating this across many, many users that is not going to hurt my overall stats. Okay. Can you think of an example, of an algorithm that we did which fits into this framework? We saw something which actually satisfies local differential privacy and not just pure differential privacy or approximate differential privacy. Any guesses on what that might be? Which of these 5 actually could satisfy local differential privacy? Yeah.
Randomized response.
Yeah, randomized response, right? Because each person is really just corrupting the data and send it across. Okay. And assuming the noise is good enough, it would satisfy local differential privacy. Right? So as an example, randomized response. Satisfies local differential. Okay. And practically, in fact, local differential privacy is the one that gets used in some applications. Like for instance, Apple, when it collects data about which emoji icons are the most used, it kind of does a variant of randomized response. Right. So when every time you type, it gets logged, but it gets logged with randomized response kind of update. Not exactly what we studied because it's not just a binary thing, but there's a variant of randomized response for multiple output stuff. All right. And especially for cell phones, data that you're collecting from phones, I think local differential privacy would be highly desired because you don't want it to kind of leave the phone maybe for some sensitive information. Okay. And the price of local differential privacy is higher. Like, even for mean estimation, we saw that randomized response was kind of not giving as good a trade-off as Laplacian mechanism. It needed more examples or more people in the database for the same accuracy and the privacy parameter, but it actually does give you local differential privacy as opposed to, central differential privacy. Okay. That's one variant. Based on many different applications, you need different variants in differential privacy. For instance, there's something called label differential privacy. The label differential privacy just means that, not all the features in my vector are really sensitive. Okay. Maybe I don't care about what my thermometer readings are, but I do care about, my smoking habits or my other habits, right? In my entire history, in my entire medical record, some features are more, sensitive than others. I don't care about some, I care about some. Can you somehow develop a notion of privacy where you can also specify, okay, column 1, the label is very special. You need to protect that. If that's the case, maybe we can get better privacy to accuracy trade-offs. That's one. Another one is called user level differential privacy. Where you imagine there are different databases, or basically a single database, but it's kind of split across multiple users. Okay, so really think of there are, maybe 100 labs. Each lab has data of thousands of patients. Okay. And now you're trying to learn something on the aggregate data, but the labs don't trust each other. Within the lab, we don't care about the privacy, but across labs, across the hospitals, we do care. Right? No hospital is going to willingly share their data with another hospital, but within the hospital, it's fine. Okay. So we have basically like, multiple sort of mini databases. Okay, so you can assume there are n users, maybe so let's say n labs or users and m items per user. Okay. There may be few labs, there may be many users per lab. What's the right trade-off in terms of the number of labs you need to guarantee privacy? Yeah.
Make sure I understand the setup correctly. So we have n labs, and for each of the labs, they all have the same users.
No, they have different users. They could have potential different users. It's almost like group privacy, except, the lab only cares about the privacy of all of these M users put together. Right? I want to say that no matter if one lab's data kind of gets changed arbitrarily, then the outcome doesn't change. Right? Because no lab trusts the other lab. You can't just say, okay, change one entry, nothing changes. I want to find out if even if my entire lab's data gets leaked, nothing should change. You're trying to, like the motivation for differential privacy is that you can incentivize each person and say, hey, look, you're not going to lose too much in terms of privacy, whether you participate in the study or not. Each individual, whether they participate in the study or not, no one learns too much about that. Now you want to go and give the same guarantee to each lab. Okay. And usually, this is kind of a new topic, you can get better trade-offs. Instead of treating it as just as a single database of, with huge records, by working with it individually, you can get better trade-offs. Yeah, and again, this is kind of driven by practical necessity. You have different hospitals, different labs, different companies, different silos of data. You want to aggregate things across them. And there are many such variants. There's something called shuffle differential privacy, where you can say somehow that there are hundreds of phones. They're sending the data to a central party, but the central party doesn't know which message is coming from which phone. Like the messages get shuffled across. Is that enough to guarantee privacy? Yeah, so there are many, many different models people have been studying, driven by different applications. It's a very, very active area of research. Okay. Any other questions? All right, so with that, let me end our discussion on differential privacy, and let's move on to our next topic. Okay. And I should say that, well, I forgot to say it at the beginning, big curve. So this is all happening in a new Scribble node. So you should go to that if you're following online. Okay. So what we're going to talk about next is a specific form of unsupervised learning, which is graphical models. Okay. So what is unsupervised learning? So when you think of supervised learning, you're basically given like, examples, labels, example, label, example, label, and we're trying to build a model that will predict the label given a new example, right? In unsupervised learning, it's a little bit like PCA. You're given a data set. You're just given a bunch of samples from some distribution, and we want to build a model for the data set. Okay. Well, what do you do once you have the model? You can do many, many things once you have them. And this is really called probabilistic models of data. Okay, so you're assuming that your distributions are coming from some family, your data is coming from, are being generated from some family, and you're trying to learn the underlying family. Okay. And we should think of, the models that we are studying as kind of in the same theme as, like, let me just say, these are like precursors of deep generative models. Okay, so we are going to study generative models, but we'll start at the very basic generative models and see how to learn them. And then, the deep generative models are like deeper generalizations. All right, and the more concrete thing that we are going to focus on is to do probabilistic modeling when our goal is not just to learn kind of a generative model for the data, but also to learn some kind of dependency or causal structure. Okay, so hopefully, once we do the definitions, it will become clear, but just keep that in mind. We're trying to, given a bunch of samples, we're trying to learn some kind of causal structure or dependency or correlations between the various features in the data. Okay. And there are tons of applications of it, which we'll talk about later on, but let's first just look at what we mean by it. Okay. So the most important concept in graphical models is independence. Okay, so hopefully you all know what independent random variables are. And if you have two random variables, x comma y, over some joint distribution, we'll say x is independent of y, which we will denote as this x perpendicular to y, if and only if for any two outcomes of x and y, their chances are, independent of each other. Okay, so the chance that x equals, the outcome of x is little x and the outcome of y is little y is just the product of the two outcomes. Okay? They're not correlated to each other. And another way to write the same thing is the chance that, the outcome of x is little x doesn't change if I condition on the outcome of y. Okay. Like, let's say if I'm tossing a coin 2 times, the chance that the first coin is heads and the second coin is heads, these are two independent events, right? Okay. So, if you think of a bunch of random variables, then you can say, I'm trying to identify sort of which features are correlated with each other. Maybe I'm trying to see, okay, is this gene somewhat correlated with some other gene? Is this chromosome, maybe somewhat, is correlated with the presence of some other disease? Then maybe independence seems like a decent notion to use, right? You can think of them as random variables and study if they are independent or not. Okay. Do you think it's a good notion or not? So it is not a perfect notion. And in fact, it can be very deceptive. As an example, let's say, maybe I'm collecting data and this is what I'm collecting and this is what I see. Okay. So I go to each person, maybe thousands of people, and I'll say, okay, do you have heart problem? Okay. And then I ask, okay, do you have, what time do you wake up every day? Okay. Maybe person one says, no, I wake up at 11 a.m. Person two says, yes, I wake up at 6 a.m. Person three says, no, I wake up at 2 p.m. Person four says, yes, I wake up at 7 a.m. Maybe says, no, I wake up at 7 a.m. and so on. Okay. So if you look at this data, what would you think? What conclusions would you draw? Yeah. Yes, but can you say that somehow waking up early and heart problems are connected to each other? Well, what do you think? Yeah.
There could be some other factor that we're not counting.
Exactly. There could be like a, what's called age, right? Older people tend to wake up early. Older people have heart problems. Younger people, like let's say if you're undergrad, then what time do you wake up? Okay. So when you only look at column by column, it does seem like the two heart problems and whether you if you compare features directly, the conclusion you would draw is waking up early is bad for heart. Okay, but that's not actually what's happening. There's really a confounder, which is the age, right? So if you want to check whether heart problems and waking up times are kind of connected, you would need to, what would you need to do? You need to somehow, yeah, go ahead. Exactly, you want to condition on age, right? You want to say, okay, given that I take a pool of people whose age is conditioned to be between 55 and 60. Is there, or maybe exactly 55? Is there a correlation between the other features? Right? So if you want to study the correlational structure, or is this gene somehow correlated with other gene, or is this gene correlated with this disease? You can't just compare the columns directly, right? Maybe you can, but it can give you misleading information, right? So this leads us to the notion of conditional independence. Okay. And all right. So conditional independence is kind of similar to before. We had 3 random variables now, X, Y, and Z, and we'll say X is independent of Y conditioned on Z. Okay. If and only if the conditional distribution of X and Y are independent. And another way to think about it is the distribution of X condition on Y and Z is the same as the distribution of X condition just on Z. Okay. So condition on people having the same age, is there a correlation between, having heart condition and waking up time? If you look at that, that might give you a good indication. In fact, perhaps the correlation will be opposite. Okay. Any questions about this? Right. So especially when you're trying to do some kind of, working with medical data and so on, looking at conditional independence and conditional correlation is very important. Okay. And you should think of graphical models as giving us some kind of, it's really a calculus of defining conditional independent structures. So it's kind of a language, of composing conditional independence things and really treating them as mathematical objects. Okay, so graphical models are distributions with constraint So these are distributions where we are going to make some assumptions about how the conditional independence relations are restricted, and then kind of learn those restricted relations. Okay. So you're going to parameterize distributions not by some kind of, okay, what's the generative model for them? Are they being generated by a depth 50 network, depth 100 network, or something like that? But more by, okay, what are the conditional independence relations that you have in them? Okay. All right. So let's think graphical models. We're going to specify conditional independence relations. And there are two kinds of graphical models. One is there's this sort of broad dichotomy. It is directed graphical models, also called Bayesian networks. Okay, and there is undirected graphical models are Markov random fields. Undirected graphical models are Markov random fields. Okay. So we'll see examples of both. We'll first start with Bayesian networks, kind of look at a classical model here. There's a very, very sort of cute and clever algorithm. We'll look at that. And when we come back to undirected graphical models, we'll look at kind of two cases and two algorithms which are more recent. Okay. But before that, can you think of one graphical model that you might have come up in other contexts? I'm sure you must have somewhere or the other. Where somehow imagine a distribution where the conditional independent structure has some restrictions on it. It's not just like you don't know what it is, there is some restriction. Reinforcement learning is one, or is something simpler even that. Reinforcement learning, I think, is many steps forward from that. But the basic behind reinforcement learning is some kind of sort of, yeah. Bandit also is more complicated than what I have in mind. Basically, future is independent of
Automata? No.
Exactly, automata, right? Cool. It's the simplest one. Future is independent of the past condition on the present, right? Markov chain. right? It's a very constrained conditional independence relation, right? I would say that's kind of the base example, right? And then you can build on this. Like, you can say, maybe I don't have a Markov chain. Maybe I have a hidden Markov chain. Reinforcement learning is kind of an advanced version where you have a state, but then you have interaction with the environment. Then you have feedback, which updates your state and so on, right? So I would say the simplest example is like a Markov chain. Okay. So you have like, variables x1, x2, x3, so on up to xn. And somehow you should think of it as kind of time ordered, right? And Markov chain means like you want to say that x4 is independent of x2 conditioned on x3, right? So in our sort of notation, you would say, maybe I'll say x3 is independent of x1 conditioned on x2, x4 is independent of x2 conditioned on x3. And there are a bunch of such relations, right? You can even say x4 is independent of x1 conditioned on x3, right? So once a condition on a node, everything in the past is independent of anything in the future, right? So a Markov chain is kind of really described by this entire sequence of conditional independence relations. That's what it is, okay? And Bayesian networks are kind of it's basically a generalization. Right? You can imagine maybe it's not as nice. Your distribution is not as time ordered like this. Right? Maybe there are different things which are coming together and then cause something. Okay. So if I were to extend Markov chain in other ways, what could I do? Any guesses? Any suggestions? Let's think of, let us be statistical modelers for now and try and extend Markov chains. Yeah. Exactly. Like, it's not necessary that, you have only one parent in some sense, right? Maybe there are like two timelines which are converging. It's not multiverse really, but like, something like that. Okay. So a Bayesian network is basically what was just suggested. Okay. So if you were to write it down mathematically, what's the object that I need to look at? So we're going to say that, I have a distribution on some alphabet. It could be zeros and ones. It could be ACGT. It could be chromosomes. It could be actual like some meta level things in your genes and so on, right? I have D features. And I want to say that there's some kind of condition independent structure in this, which is a generalization of the Markov chain setup that we saw. Okay. What object can conditional probabilities, but like, I want something sort of pictorial or graphical, right? If you think of Markov chain, it's a path. And what else? Yeah.
Directed acyclic.
Exactly, directed acyclic graph, right? You can have any graph, but you don't want cycles. Right? Cycles don't make sense if you want to say somehow x1 kind of is, before x2 and then x3, but then you go back, there's like time travel, right? Doesn't make sense. Okay. So a Bayesian network is basically parameterized by a directed acyclic graph. Right. So we have a directed acyclic graph or DAG, meaning a graph with directions on the edges, and there is no directed cycle. You can't go from 1 to 2, 2 to 3, and 3 back to 1. Okay. On D vertices, the number of features, many vertices, G. Okay, so we are given a directed acyclic graph on D vertices G, and we will say a distribution with D features is a Bayesian network. Sometimes it's also just called a Bayes net with graph G if the following holds. Okay. So it's best to, I mean, there is a formula, but let me illustrate it with an example. I think that's the best. Okay. Let's think of the example first. Let's go back to the Markov chain example. So if I give you the Markov chain like this, then this is a directed acyclic graph. I have D vertices, and the directed acyclic graph is just a path from left to right. Okay. And what's the formula for the joint distribution of this? Can I write it in some succinct kind of seemingly simpler way? Can I break up this giant density, giant distribution into smaller pieces? Yeah.
As a quantification of probabilities.
Exactly, right? The simplicity in Markov chain is that the conditional probabilities are actually simpler, right? The distribution of the last one, conditioned on everything else, is just whatever you get from conditioning only on the previous one, right? So if you go back to a notion of conditional independence, I would say this interpretation is actually the more useful mathematical, right? Saying conditioning on two things here is really the same as just conditioning on one thing. Okay. And for a Markov chain, if you have something like this, it would be true that conditioning on everything before would be the same as just conditioning on the node before you, just before you, right? Because the future just depends on the present and not on the past, given the present. Okay. So what you get here is this nice formula. I can write it as the first node is completely arbitrary. We don't have any control on that. Okay. And then we have times okay, this is what you have when in the case of a just the Markov chain. All right. Maybe, okay, so now let's say I tell you that the conditional independence structure is something else. Okay, suppose I have something like this. What could you, how could you potentially break up the distribution again? Take your guess and we'll see if it's correct or not. Right? And I want to say that the conditional independent structure is somehow like this. So 3 kind of depends on 1 and 2 kind of depends on 1, but 4 it depends on 2 and 3, but if a condition on 2 and 3, it should be independent of 1. Okay. So you can think of it as some kind of timeline. Then I can say the probability that x equals little x1, x2, x3, x4. How could I break this up here? Any suggestions? Once again, like, 1 is maybe standing on its own. Yeah. Actually, I want to say it just depends on 1, right? These are 2 kind of occurring separately from 1 and independently, right? And somehow they then come together to affect 4. Okay. So each node essentially is conditionally independent of things which are not its parents. So you can think of this notion of parents, right? For every node, there are its immediate parents, which kind of link into it. And the conditional independent structure is entirely determined by the graph. Okay. Does it make sense intuitively? And mathematically, you'll say that a distribution D is a Bayesian network with the graph G. Right? He has some directed acyclic graph, and I can define a distribution as so I should be able to break up this distribution as a product of individual conditional probabilities, but I don't have to condition on everything before. I just need to condition on the parents of each node. Okay, immediate parents, just the 2 immediate parents or 3 immediate parents or how many ever parents you might have. All right. So for instance, for Markov chain, it's saying, okay, the parent of 3 is just 2. So that's why we're only conditioning on 2 here. For 4, it would just be 3. For 1, there is no parent, so you're not conditioning on anything. Okay. And the same thing here. So 1, there's nothing. 2, the only parent is 1. 3, the only parent is 1. 4, 2, and 3 are parents. Okay. Any questions about this formulation? Maybe as an example, right? You can say, okay, maybe. Okay, so maybe you do something like, let's say, if you have smoking history, that's one kind of variable you could keep track of. And then maybe another thing you keep track of is you do a chest X-ray and there is a flag. Basically, you notice something in the chest X-ray. Right? You went from these 2 things, but the lead up between these 2 could be different. Okay. I mean, in between, you can have, maybe if you have smoking history, it increases your chance of getting like lung cancer. At the same time, there are other diseases you could potentially have, right? Maybe you have bronchitis, Okay. And depending on whether you have bronchitis or lung cancer, they can affect what's the chance that your chest X-ray comes out positive. Okay. This could be one dependency graph. As another example, maybe you'll say, maybe you stayed up all night yesterday, and then as a result, you wake up late. But on the other hand, maybe independently, there's a traffic jam, and both of those could cause you to late to office. Okay, you can imagine, I mean, these are toy examples, but really think of graphs which are millions of variables. You have millions of chromosomes, millions of genes. You're trying to decipher, is there a sort of nice underlying conditional independent structure? Okay. So that's the definition of Bayesian networks. It gives us a nice language for us to talk about conditional independence questions. And by and large, maybe the central question in the area, there are two central questions in the area. Okay. One is, imagine you're given n samples from this distribution, right? You have n samples from the Markov chain. You have n samples from some distribution generated by with some underlying Bayesian network. As a learning question, you can ask, okay, can I, reverse engineer and figure out what is the graph that explains this? Okay, we don't know the graph. We're given the sample, but we're trying to learn the underlying sort of this causal or dependent structure. So the output, maybe I'll just say, learn. The underlying, I should say, directed dependency graph. Okay. Or maybe you can say, that's one goal. And then I also want the right conditional distributions. Okay. So there's two goals. Like, I can say, I don't know the underlying directed dependency graph, and I can try and learn that. Or in some cases, like, you assume you know the underlying dependency graph, and you're just trying to learn the right conditional distributions. Okay. For some applications, one is more complicated than the other. For, I think, genetic data and so on, often this could be one of the main challenges, right? And for some applications, this is the right challenge. Okay. And there could be a middle ground. Maybe you have some inkling of what the graph might be, right? If you think of something like transformer architecture, you are assuming that there is some kind of Markovian structure where it's going left to right. You have the tokens and you're combining them, but you're not fixing yourself to just a plain Markov chain, right? You do LO kind of correlations back in the past and so on, but they're kind of structured correlations. Okay. But in all of those applications, you're trying to learn what's the right conditional distribution. given the first 10 tokens, what should the next token be? And then what's the next token given the first 11 tokens? What's the next token given the first 12 tokens? Okay. All right. So what we'll start talking about next is when can we kind of meaningfully solve this question? And what's the sample complexity that I need? How many samples do I need? Can I always do this? Do I have to place some restrictions and so on? Okay. All right. So we already saw the example of a Markov chain. And the next thing I want to say is, if I just tell you, okay, I have a distribution which has a dependency graph and go learn it, that's a very ill-posed problem. It's not a meaningful question because, can you think of a reason why it's not a good question to ask? If I give you an arbitrary distribution, is there a dependency graph which explains it? Yeah. Exactly, right? For any distribution, there is sort of a trivial dependency graph, conditional dependency graph. Okay. For instance, let's first start with something numerical, kind of an equation, and then draw it as a graph. Okay. So by the chain rule of probability, I can break up any distribution as something like this. But I can keep going like this. Every time I add a single variable and condition on the entire past. This decomposition is true for any distribution. There is no restriction on when this would apply. Right? So this is chain rule of probability. I can break up any arbitrary distribution as a sequence of products where I condition on all of the previous ones. In fact, this is forms, kind of the basis behind the naive Bayes classifier and so on. Okay? But pictorially, what this means is for any distribution can be written as a graphical model with the following graph. Which graph would this correspond to? Would this decomposition correspond to? It has to be directed acyclic, but I want to say, okay, there's a simple way to write it as a directed acyclic graph. Yeah. Exactly, right? For any distribution, I can say, okay, 2 depends on 1, 3 depends on 2 and 1. 4 depends on 3, 2, and 1. Right? Basically, just add from edges from every vertex to everything subsequent to it. Okay. So this is a valid sort of base net for any distribution. So it's not a well-posed question at all if I don't place or any constraint. Okay. And it also makes sense that you cannot learn arbitrary distributions with finite samples. You can only learn, if you place there is some simplicity in the distribution. Right? There's some generative process, there's some structure in it, otherwise you should not be able to learn. Okay. So this is a dependency graph, or let's say a base net for any distribution. Okay, so our goal of learning distributions based on their base net formulation is not meaningful without further refinement. Okay, can't just say, okay, you're seeing samples from a Bayesian network, go learn it. That doesn't make sense. So what else can we do? Any suggestions? What would be interesting questions? Well, think of the Markov chain example, right? You said, okay, it depends only on the present, like in a previous state. Maybe you can simplify it and say, okay, maybe it doesn't just depend on the previous state. Maybe it depends on maybe 2 days history. Or maybe like, you go back 10 days, but not like, forever in the past, right? Or you might say, okay, maybe there's some kind of, you can draw the graph in some nicer way and that would still be fine. Okay. So one way to try and sort of fix this is basically limit the graphs allowed. So let's say structural assumptions on the graph. So we're going to restrict the kind of graphs that are allowed. This is, maybe not an arbitrary graph, but still, if I have 1 million features, then the max degree in this graph is also 1 million, right? The last node is connected to everything in the past. Okay, and it's, in terms of drawing, it's a very complicated graph. Okay. So people have studied cases where you kind of, let's say, place some structural assumptions. Assume the graph is simpler in some way. Maybe it's just a path, or more generally, you can say I'll limit the degree. Like in degree of vertices is bounded. Okay, maybe I'll say for each vertex, it only depends, there are only 3 parents. Okay, maybe there are only 4 parents, 2 parents. They could be somewhere in the past, they could be wherever, but there are only 2 edges which are incoming. Or you can also say the graph doesn't look this arbitrary. It's somewhat nice. Maybe it's like a path with few edges going back, or kind of a modification of that. Or you'll say some properties of the graph. And maybe you'll say the graph looks in some way, maybe I can draw it nicely on the plane. Okay. Maybe the base structure is that it's going from 1 through D, but each node has one sort of outlier edge going way in the past. Okay. So now it kind of becomes meaningful. I'll tell you that the true distribution satisfies some such structural property. And then we can ask, okay, can I learn it in this case? Can you learn the dependency graph when you have such nice assumptions? Okay. So generalizing the Markov chain, what would be some nice properties of the graph to have? Any suggestions? Actually, even in the Markov chain case, like, suppose I tell you that it is a Markov chain, but you don't know the order. Can you learn the order? That's also interesting. But what could be a more sort of, a further generalization than just a path? Now think of the simplest graphs you might have seen. What's the simplest graph? Which is connected? Markov chain is simple, right? But if just in terms of graph theory, what are other graphs which are simple and connected? Like a path is one, but what else? Yeah.
Bipartite graph?
Well, bipartite graph is actually still more complicated. Like the simplest connected graph is probably a tree. Right? There are no cycles, directed or undirected, right? And it's kind of really telling you something like, okay, there is maybe a sort of timeline. Some things are happening simultaneously, but you have kind of independence across that. Okay, so just as an example, so trees, paths, maybe I'll say grid graph, and so on. Like, you can place structural assumptions on what the graph could look like. And the bounded degreeness is also sometimes helpful. Like, you'll say maybe the degree is just 2. Can I learn it in that case? Okay. And that's what we're going to talk about next. In particular, we'll focus on sort of the main challenge. Learn distributions under assumptions on okay. So the bounded degreeness is one assumption. It's actually not that helpful. I mean, it is helpful, but not in all cases. The case of a tree, on the other hand, is very nice, and that's what we're going to study. Okay. So what if the underlying base net is a tree? Okay, so meaning I have something like my graph looks maybe like this. So tree just means that once they split up, you cannot come back together because that's a undirected cycle, right? So you're not even allowing undirected cycles now. So you should really be splitting further. You cannot have an edge like this. That's not allowed. Okay. And you can think of it basically as the timeline is splitting, but they do not merge back. So what if my true distribution has a dependency graph that looks like this? Given samples from this, can I go back and learn the dependency graph? I don't know what the tree is. I just know that there is a tree underlying it. Okay. So let's take a 5-minute break, and when we come back, we'll study this question, and then we'll see a sort of a beautiful algorithm from actually like maybe, how old is it now? 60 years old, 65 years old. Okay, we'll look at that. Okay, so let's take a 5-minute break. Okay, so sort of the classical question in this area, and I think it's a very nice question, is the following. So this is called the Chow-Liu algorithm from 1968. And what it showed was that we can learn tree-shaped Bayesian networks. Okay, so that's what we're going to see. We are looking for structural assumptions on networks which can make them kind of learnable with good algorithms, and being a tree is one such thing. So let me be more concrete. And so what we have is, so what's this setup? So the input for us is samples x1, x2 up to xn from some d-dimensional space, right? Samples from distribution D. Okay. And the assumption which is the main deal here is that D has a Bayesian network which is a rooted tree. Yeah, I mean, the rooted part is not exactly necessary, but it kind of makes things simpler to handle. So let's just do that. So rooted tree just means that each node has a single parent, right? You know, something is just this really. It's just a fancy name for saying each node has a single parent. Okay, going all the way back, and there's one node which doesn't have a parent. Right, so there is some root which has no parent, and every other node has exactly, you know, has at most has one parent. Okay, this would be a rooted tree. Okay. So rooted tree means every node except root has a single parent. Okay, so Markov chain is definitely a Bayesian network whose network is a rooted tree, right? It's just a simple fact. Okay. So as an example, Markov chains definitely fall into this category, right? So you can have a 1 going into 2, going into 3, going into 4. Okay. And you can also have something like maybe 1 which is going into 2, which is going into 3, then maybe 1 directly cuts into 4. Okay, so in the second case, what do I have? I have probability x equals x1, x2, x3, x4 is okay, right? And we're asking, okay, you are given samples from such a thing, and what we want is, and as we discussed earlier, you can ask for 2 goals. Output the true tree, output the right conditional distributions. I mean, tree structure seems like a pretty strong constraint, but you know, it's not that. There are situations where it is reasonably common. Like if you think of some kind of gene mutation, sometimes the mutations happen on a single gene, right? You're tracking how the mutations are progressed, you mutate, and then that kind of branches into some other mutations, other mutations and so on. But in some simpler cases, you don't have cross combinations, right? In such a case, you would indeed get a tree in how the mutations are propagated. Okay. And these 2 goals actually have different names given how commonly they come up. The first goal is usually called the structure learning problem. Okay, so your goal is to learn the structure of the underlying graph or the tree or whatever graph you have. I want my main thing that I'm interested in is the conditional independent structure. Maybe the true actual formula is not as important, but knowing the correlation is what I really care about. Okay. And the second goal is called parameter learning. Okay, meaning I want to even learn, okay, an approximation for each of these conditional distributions. And whatever model I have, I want to even know what are the parameters which define it. Okay. All right. And so if I'm trying to learn the parameters, you might wonder, can I learn the parameters exactly? What do you think? Can I learn the distribution exactly? With finite samples, it's usually not possible to learn the distribution exactly, right? Even if I'm tossing a coin and I want to estimate its bias, and if I only have finite number of samples, I can't know the bias exactly, right? I'll only learn it up to some error. But defining error now is a little bit complicated because we're talking about distributions, right? If you're talking about numbers or predictors, your real numbers, you can define a loss function and then just kind of compare them and so on. Okay. So we need to define a notion of goal, learn a distribution d prime such that the distance or the error between the true distribution d star and d prime is small. I didn't use star before, so let me use just d. Okay. So that's what I'm trying to do. We want to learn a distribution such that the distance between what I learn and the true distribution is small. Okay.
Like, is that always doable? What is that you're talking about?
Right, for sure. I mean, that's why we're kind of assuming that there's a simple structure behind the distribution, right? It's simple enough that we expect the distance can be computed. In fact, that's one of the reasons why you have to make the simplistic models. Okay. And the notion of distance that, okay, so you must know, maybe you've seen some notions of distance for comparing distributions. Do you know any? If you're talking about vectors, you can talk about L2 distance, L1 distance, but for distributions, those things are, not as good.
L divergence, but also that it's not.
Right. So actually, KL divergence is not a distance, but that's the one that's actually most useful when talking about distributions. In ML power lenses, scale divergence is basically the same as cross entropy. Okay. So when you say you can try to learn things with respect to cross entropy loss, you're basically trying to minimize the KL divergence. The KL divergence came up, in information theory in the 50s. So it measures how close two distributions are. Okay. And there is a formula for it. It's essentially, as I said, is the same as cross entropy. And if I have two distributions, P and Q, the KL divergence of P over Q is, it's not a distance because it's not symmetric. When we think of distance, usually we think of it as symmetric, right? When I swap the two things, the distance should not change. For KL divergence, that's not true, but that's okay. So the formula is, for every possible sample point in your, for every possible event in your sample space, you look at what's the probability under the distribution P multiplied by this weird looking expression. So this is the cross entropy loss essentially, or if you know entropy, it's kind of connected to that. So it's P of A times log of Q divided by P. Okay. So I'm looking at the ratio between the two probabilities, but I'm taking the log and expectation with respect to P. Kind of a weird looking formula. Why this is so natural, or why should you study it? That's a long story. This was introduced basically by Shannon in the context of information theory, but it's a very important notion. Okay, so this is the probability that A happens under P. Okay. And oops, actually I wrote it wrong. They should be P, this should be Q. Okay. And it's called cross entropy for the following reason. If I expand it out, what am I getting? It's P of A times log of the ratio of two things is the difference of log. Like log of A over B is log of A minus log of B. So I can write it as this minus log of Q of A, which is summation A P of A log base 2 P of A minus summation A P of A log base 2 Q of A. Okay. And this is the entropy of a distribution. If you know information theory, there's a way to quantify how much uncertainty or how much randomness a distribution or a random variable has. And going back to Shannon in the 1940s, he introduced this notion of entropy of a random variable, which is P of A times log of P of A. And in KL divergence, you're basically looking or comparing kind of what you would get by replacing what's inside the log with the other distribution Q instead of P. Okay. Any questions about this? That's why it's called cross entropy. Like somehow I'm exchanging P for Q and looking at it. Okay, it's related to cross entropy. All right. And as an example, let's say let's say my sample space is just 0 and 1. The first distribution is let's say okay, so maybe P of 0 is half, P of 1 is half. So maybe the first random variable P, my first distribution is uniform between 0 and 1, and Q is maybe, let's say, 1/3 and 2/3. Okay, so one is a little bit biased, one is not biased. All right. Okay, so what is scale divergence between P and Q? And compute it as basically P of 0 times log of P of 0 divided by Q of 0 plus P of 1 times log of P of 1 by Q of 1. So which is half times log of 3/2. Okay, half of log of 9/8. Okay. So one thing to keep in, I kind of notice here is what is the sign of log of 3/2? Is it positive or negative? Positive. How about sign of log of 3/4? Negative, right? So we are adding a positive number and a negative number, but we got a positive number, right? And usually when we think of distances, we want them to be kind of symmetric, but also more importantly, we want them to be positive numbers. Okay. And it's not very clear, at least from the definition, if this is going to be positive, right? Because you have some negative numbers that you're adding as well. Not every component is positive. Okay. But it turns out by kind of some nice convexity arguments that scale divergence is actually always okay. So it's an amazing and very important property that KL divergence between any two distributions is always non-negative. And in fact, it's equal to 0 if and only if they are identical. Again, distance means it's non-negative, and when their distance is 0 means they should be equal. Okay. At the very least, it satisfies these two properties. All right. And now that we have the notion of distance, scale divergence, we can formulate our question again. So what's the algorithmic question that we are studying, right? So what Chow and Liu studied was the following. We are given access or the ability to generate samples from a distribution. Let me call it P star on sigma to the D. Sigma is some alphabet. As I said, think of it as just 0, 1, if that helps, or you can think of that as ACGT or some other metaspace. Okay. Generated by a base net on a tree P star. Okay, so I'm getting samples from some distribution P star, the unknown true distribution. Okay, and it has a base net which has a true tree T star. Okay. And what is our goal? Our goal is to find a tree T and a corresponding base net PT, okay, such that the two are close. Okay. Find me some other base net, which also is a tree. We know that the true distribution is a tree. So hopefully what you learn will also be a tree. Find me something like this so that what I learn, PT is kind of close to P star within some error epsilon. Okay. Make sense? Yes or no? Yes. I mean, if you want, you can think of it as like, really someone is generating data by a Markov chain, but then they scrambled up the order for you. Can you sort of reverse engineer and unscramble the data and learn it? You have some time series data, but you know, the data was shuffled somewhere. The coordinates are lost. Can you recover the true order? Okay. So maybe as an example, you can think maybe this is what T star is. Okay, just, you know, maybe this is what T star is. We don't know what it is. It's hidden from us. Okay, but we do see samples of the form x1, x2, x3, x4, x5. Okay, we see samples like this. Okay. Given samples like this, we want to go back to recovering this tree. You know, how would you go from one to the other? Any suggestions? Like, you know, what could make us sort of identify the right tree structure? Any guesses? Yeah.
By writing down different argmax.
Right, but as a quantitative formulation, I think that's very good. Okay, so suggestion one is, you're saying basically there are two things that we have to do. Actually, I think let's work with that. So you want a tree, you're kind of enumerating over trees, but also given a tree, there are different conditional distributions you might have, right? And then you'd say argmax, you know, distributions with T as the base net. Actually, maybe we should do min, right? You know, we're trying to minimize the distance, right? So, you know, this okay. So you have T and then distributions PT with T as the base net of the KL divergence between P star and PT. Okay, you know, we would like to do this. Well, we don't know what P star is. So, I mean, as a function itself, we cannot compute this function exactly. But you might assume, you know, maybe we're given samples for it, so we can do something, but even that's not clear, right? How, if just given samples, how can I estimate the KL divergence? Is that something I can do? I'm not sure, right? So it's not even clear how to approach it, given that we don't know what P star is. That's the whole problem, right? We only have empirical access to samples and nothing else. Okay. Any suggestions, you know, on how we might kind of get around this or approach this? Yes, no. Okay, so let's maybe break it up into two pieces. Yeah.
That give us between the divergence every single possible.
I mean, the support could be everything, right? You know, for every conditioning, support could be everything, right? So it might not help us to look at just the possibilities, right? The possible, maybe everything is possible, but it's the relative odds between them which tells us the right dependency structure. Okay. So, I mean, it seems like a pretty complicated thing, given I can't even estimate this function. I don't even have like an empirical estimate I can draw for this. Okay. Right. Yeah.
maybe you could try to estimate the pairs of tendencies, like pairs of.
Right, so that's a good suggestion. I mean, you can say maybe let's try and estimate the dependencies between pairs, but first, we had to be a bit careful because we saw that conditional independence could be very different from pairwise things, right? So, and the only thing that we know is the conditional independence. Right? But as it turns out, you're right. Okay, but it's okay to do pairwise comparisons when you have tree structure. If you don't have tree, if it's a more complicated DAG, it doesn't work. Okay, but before that, so there's two optimization parts here, right? In some sense, there's a tree that you have to optimize over, and then you have to choose the right conditional distribution to optimize over. Okay, so let me simplify my task and say someone came up to me and said, okay, you know what, I'm going to make it a little bit easier for you, and I'll tell you that this is the true tree, or this is the tree that you work with. What is the best conditional distribution to choose? Okay. So let's make it simpler. As an intermediate step, let's break it up into two pieces. We have a free key to work with. Okay. Go find the best conditional distributions to form. Okay, so let me rephrase. We made it a little bit simpler for us now. Okay, maybe it's a different overkill. So let me copy it. Okay, we are now saying we're given samples from P star. And we are also given someone also told me a tree T to use. Okay, go ahead. I think this will be the tree that will work. Find PT with basenet T such that that minimizes KL P star. Given that this is the only structure you can use, what is the best setting of the conditional probabilities that will minimize the KL divergence between the true unknown distribution and PT? Okay. We just made it a little bit simpler, but it's still not clear how to go about it, right? Because we don't even know how to estimate this guy even now, right? But we'll see that when both the distributions are trees, like KL divergence, you have P and Q. When both the distributions are coming from Bayesian-nets, which are trees, you can estimate it in a very nice way. It's not true in general. You need both of them to be trees, but when both of them are trees, there's something nice happening. Okay. And that will lead to the algorithm on, later a nice formula here, which will help us fix the tree and everything else. Okay. All right, so let's take it up from here in the next lecture.